phase diagrams are a nice way of giving us the ability to predict what state of matter something will be in under certain conditions. So the way a phase diagram works is, because both pressure and temperature affect the state of matter, if we graph that, then we can find any point on the graph. If we're at a certain pressure and a certain temperature, we can find that point on the graph and determine the state of matter. So if I'm at a pressure of, for this particular substance, each substance has its own phase diagram, but for this particular substance, if I'm at a pressure of, 10 atmospheres, I'm at a temperature of negative 100 Celsius, then the state of matter is a solid. Right, so I can use the phase diagram to determine what the state of matter will be for a substance. I can also use the phase diagram to find points where substances or different states for the substances will be in equilibrium. So there's a line here where if I create a temperature and pressure that puts me right on that line, now I'm at an equilibrium between solid and liquid. That'd be like a melting point. That'd be like where the rate of melting is the same as the rate of freezing. So the quantity of solid and liquid I have at that temperature and pressure isn't changing. There's also a triple point, where if you're at just the right conditions, you can have solid, liquid, and gas all in equilibrium together at the same time. And that the rate of the solid converting to the liquid and converting to gas is the same as the rate of the gas condensing back to a liquid and reforming the solid. And so you have the amounts of solid, liquid, and gas not changing over time if you maintain those conditions at the triple point. So let's look at the phase diagram of water, a familiar substance. So what we can see here is the triple point for water is close to 0, and it's a very low pressure. Right? So to get water to be a gas at a low temperature, you need a really low pressure, right? Because the pressure of the atmosphere hitting down on the surface of a liquid or solid kind of holds the molecules in. If you take that away, then substances will boil at much lower temperatures than normal, and they'll melt at much lower temperatures than normal. So if you have water at 0.006 atmospheres, which is a fraction of the atmospheric pressure, the water is not much holding the water molecules down. So some of those water molecules, when they break their attractions, they just float away. There's no collisions holding that down and helping it to reform attractions. So at that particular temperature and pressure, you get both water in the form of ice, liquid, and vapor. We can also use the phase diagram to tell us normal boiling point and normal melting points. Normal means you're at 1 atmosphere. So if you are at 1 atmosphere and you raise the temperature up, you get a conversion from solid to liquid when you're right at 0 Celsius for water. So water only freezes and melts at 0 when you're at 1 atmosphere pressure. If you change the pressure, the melting point will change. And then if you keep increasing the temperature until you get to 100, that's the boiling point, because that's the point where the liquid and vapor are in equilibrium. Again, if you change the pressure, the boiling point will change. So if I say normal boiling point, I mean 1 atmosphere pressure. If I say, what's the boiling point of water at 0.5 atmospheres of pressure, I would have to give you more graduations on here so you could find the 0.5, but if I gave you that and you could see where the 0.5 was, you'd bring this over, and then you'd say, okay, that's where the phase change is between liquid and vapor. That's my boiling point. So what temperature should it be? It'd be right here. And you'd need more graduations on there, but you could estimate maybe it looks like it's about 75 or something. It's boiling at a lower temperature when you have a lower pressure. And so let's look at examples. There's a couple examples in the textbook that we can just run through here. So here I've got a phase diagram. This is not water, it's some other substance. First thing we want to do is determine the normal boiling point. So what we'll do is normal means 1 atmosphere pressure. So the normal boiling point is going to be the temperature at which I'm in equilibrium between solid, liquid, and the normal boiling point is the temperature at which I'm in equilibrium between liquid and gas when the pressure is 1 atmosphere. So that's going to be about 200 there. The normal melting point is when I have equilibrium between liquid and solid. The normal melting point is when I'm at 1 atmosphere, so the temperature required to be at that position is going to be about 130. So under normal conditions or 1 atmosphere, you should be able to determine the freezing point, which is the same as the melting point, or the boiling point. I might just give you some other random pressure and temperature and ask you to determine the state of matter. So if I tell you the pressure, you find that. Tell you the temperature, you find that. You go up, go across. Okay, those two meet in the solid phase, so it means under those conditions, whatever the substance is must be a solid. Also, I will expect you, so I might give you a phase diagram where the solid, liquid, and gas are not labeled. So you should be able to label those. The solid will always be on the left, because as I lower the temperature down, things tend to go slower and form more effective attractions, which is what we have in a solid. So the solid will always be on the left, and then if you can find an area where 3 are all on the same horizontal line, the liquid will be next and the gas will be last. And so you can rationalize that. You could say, well, also if I lower the pressure and I don't have as much atmospheric pressure beating down on the surface, it's going to be easier for these attractions to break and for the substance to evaporate. So even at a low temperature, when I also have a low pressure, I expect to see gas. I also might ask you to identify the triple point. So you find the point where all 3 meet, solid, liquid, gas, and then you determine the temperature and pressure necessary to get to that point.